Okay, it's my pleasure to introduce Peter Jipsen from here and
Here, there, and everywhere.
and one of the few that we owe a big debt of thankfulness for organizing this wonderful conference. So Peter is going to speak on partially ordered algebras and pre-clones.
Thank you. It's a pleasure to speak here at BLAST, and I really enjoyed the BLAST conference series enough to be part of organizing two of them. And this is also, I should say that, it's joint work with Erko Letonen and Reinhard Paschel, and it's been a great pleasure to do this research in the last half year when I was on sabbatical, and it was something that began when I gave a talk in the PALS seminar that was organized by Peter Meyer to keep us sane during the pandemic. And so it's, well, here's sort of the outline of what I want to present. I'm interested in partially ordered algebras. I'm going to try and say something about clones and pre-clones and what we call S pre-clones. And then there's a nice Galois connection as for ordinary clones. And it leads to a lattice of S pre-clones that we're still interested in investigating much further. So some parts of these slides are going to be quite technical. I know it's late in the afternoon. The slides will be available, and eventually we might have a preprint. And so, great, let's get going. Partially ordered algebras. For uni-sorted universal algebra is something that's been developed extensively, and it's also very well represented in categorical terms. The central concepts, we've heard them in Cliff's talk very nicely. It's all based on a set. And now, instead of basing the algebra on a set, we would like to base it on a partial ordered set. And so the partial order, I put it right after the set A, and then there's the fundamental operations. And for any poset, there's a dual, which will be denoted by A dual. And a fundamental operation symbol corresponds to an operation on A in a partially ordered algebra that has to be order preserving or order reversing in each argument. So this is a restriction on what fundamental operations one wants to consider. And normally when you talk about partially ordered algebras where there's been a lot of work is when it was only order preserving. So I'll say more about that. The information about whether it's order preserving or order reversing is considered to be part of the signature. So you record that together with your fundamental operations. This can be expressed with quasi-identities using, well, not quasi-inclusions, I should say, using the partial order. And then there's the concept of partially ordered variety, etc. But here's the notation that we use, this F superscript lambda. The lambda is to give this information about the signature, or signum as we call it. And it's just some sequence of pluses and minuses in the case of this simple partial ordered setting. And then it just means that if it's positive in one and negative in the second argument, then as a function from A cross A dual to A, it just has to be order preserving because we've turned one copy of the poset upside down. So this is the standard algebraic setting, and then you can, so the base category of sets is replaced by the base category pos. And the problem is that the term operations are not necessarily morphisms in pos because order reversal is not order preserving. Normally the morphisms are just order preserving ones. And what's worse is when you identify two arguments where one is order preserving and the other one is order reversing, then it may end up being a unary function in this case that's neither. And this actually happens. And so the clone of operations is no longer displaying this property. And so the whole thing seems to depend on what are your fundamental operations. And the point of this course is to try and, of this talk is to try and fix that. So varieties of algebras with order preserving operations only were studied extensively already, also in the categorical setting. And in algebraic logic, that's not enough because the order is basically some kind of consequence relation based thing on the terms. And the operations in logic that you care about also have some negations and residuation implication things. They are not order preserving in all arguments. So this general study is a part of algebraic logic. Don Pigozzi was heavily a part of that algebraic logic. In general, is something Hedlock and Pigozzi wrote the base monograph for this area, and later then it was extended to this part. And this is some lecture notes, a technical report that hasn't been published yet, but it's well worth reading. But now, what is a good, the set of term operations on an algebra form a clone, or in categorical terms, it's a Levere theory. What is a good notion when you do this over partially ordered algebras and you want the order reversing things also to matter and be part of that? So, well, let's go over some background notation. The operations on A, that's all the n-ary operations, and then you union them together. Let's S be a fixed monoid. S is the monoid of these signa that tell you whether something is increasing or order preserving or order reversing. And so in general, this would be a finite set S. The monoid identity, I'll write it as E, and the S operations on the finite set, or any set really in the setting there, is just the union of all the n-ary operations, each paired with one of these signa that tell you that it's an n-ary operation and what the coordinates are doing. So this pair F comma lambda is also written as F superscript lambda to be a little bit more compact. And for example, the monoid could be this set with plus and minus in it, and the identity would be the plus, because plus times plus is plus, plus times minus is minus, and of course minus times minus is plus in this setting. So that's actually a two-element group. And then you have here an example of something which is order preserving, or just plus signum in the first and minus signum, because they don't have to be tied to a specific order. This theory is more general. And here's the notion of S pre-clone. So first of all, I haven't even told you what a pre-clone is, but this is an example of a pre-clone. And S here, you can, well, one way you could think of it, if you want to be in standard universal algebra, you can just take S to be a one-element set. And then there's only one signum, which is everything behaves the same way. And then this will be the definition of a pre-clone. And in fact, it'll be the definition of a clone in the style of Reinhard Peschel, and where you say, okay, it's a set of these S operations, and it will be an S pre-clone if, first of all, it has to contain the identity with the signum of the identity element of S, which would be plus in the special case that we're mostly interested in. And then the set F has to be closed under 5 operations. The first 2 really just tell you that you can permute arguments, but you also have to track the signum correctly. And then Nabla superscript S says that you can add a fictitious argument in the first place with signum S. In standard clone theory, you just add a new first argument, and you don't have to say what kind of argument it is. And then delta identifies the first 2 arguments. But here is the part that makes it a pre-clone rather than a clone, because you can only do this if they have equal sigma. So you're not allowed to identify arguments arbitrarily. And in a clone, you could always do that to any arguments. I mean, term functions, you're allowed to substitute x in for everything, and that's a new term. Here, you cannot do that because we want to avoid substituting x in for order preserving as well as an order reversing argument at the same time. And then composition for n-ary operations, in this setting, you just say how you compose a function into the first argument of another function. And the signum tracks this with the monoid operation of S. So this is where if you take a function that is order reversing and you plug it into an argument that is order reversing, then those two get combined by the monoid and tell you that now it's order preserving. Okay. So examples of S pre-clones make the monoid trivial monoid, and it will be just a clone. Make it a plus minus monoid with this group setting, and then all the operations that have this nice property of being order reversing, order preserving in each argument form an S preclone. It's called the plus minus preclone. And you also have the largest one, which is all these operations. So there's some operations in there that have the same effect as a function, but they have different signa. They all just thrown together, and it happens to satisfy the previous definition. And there's also the smallest one, which comes from the projections, expanded with any signum as long as if the projection is onto the ith coordinate, then the signum in the ith coordinate has to be the identity of the monoid. And those are all called trivial S operations, or S projections, I guess would be the name. And then you have the concept of a S preclone that is generated by a set of functions. So it's nice because all the concepts from clone theory or Levier theories extend to this setting of having a theory which isn't even universal algebra, strictly speaking. It's relational structures, because you have this ordering in there, or additional things. It doesn't even have to be an order. And so now we just want to look at the concepts of clone theory: relations, polymorphisms, invariant relations. These are central to how people study clones and the basis for the Galois connection. So you have an operation, n-ary operation, and the m-ary relation. And if you take m tuples in the relation, and let's consider them as column vectors. This is we prefer this. Reinhard is part of our group, and you can do it in two different ways, of course. But here, think of these as columns, and then the function gets applied to the rows of what is essentially something that you should think of as a matrix. And F preserves row, written with this right triangle notation, if, when you have all these columns from the relation, then applying the function to these columns row-wise produces a new column, the F's of all these inputs, that is in the relation row again. That's just clone theory, and it says that the function preserves a m-ary relation, n-ary function. And then F is called a polymorphism of row, and row is called an invariant relation of F. And this relation right triangle is a basis for a Galois connection that on the one side you have the Galois closed sets called polymorphism sets of a set of relations, and on the other, all possible relations, m-ary, everything's finitary in this setting, and invariant relations of a subset of operations. And then, for example, if you look at the polymorphisms of the less than or equal to relation, that would be all the order preserving relations that already occur in normal clone theory. But in our setting now, you have the same notions, but with the S in front of them, and S stands for the monoid. And you have this concept of S relations. This is the interesting thing is, it's not a single m-ary relation, it's an S tuple of m-ary relations, and then the union over all m. But the relations in the tuple, they all have to be m-ary for the same m. And then you say that a function with a signum lambda preserves such a tuple of relations if, when you take all the columns from, and now you have to index these, and they are slightly shifted by, this is the monoid operation. Lambda 1 is the signum of lambda in the first position, multiplied by S, and this implication has to be true for all S. So this is a bunch of things that have to be true for every S. But the monoid is usually finite, so it's not this universal quantifier is on the other finite list of things. And you can abbreviate this to make it more palatable as, and this is standard notation also in clone theory. You just say that the function F is operating on all these relations and produces something contained in row sub S. That's the S component of this S tuple of relations. And on the input side, it depends on the signum, what you're allowed to put in. Like into the positive coordinates, you put row pluses. So if S is plus minus, then this means exactly that here you put the row pluses on the positive coordinates, the row minuses on the negative coordinates, And first of all, you have to be in row plus, and then you switch everything around, because here you multiply it with a minus sign, and the minus sign flips everything, and then it has to be inside row minus. And this is when, Reinhard explained this to us, and it was like, wow, yeah, this looks exactly like what we need, because that's what it means to be order preserving or order reversing. And so if a function is preserves less or equal to comma greater or equal to, that's the condition. So this is a very special case. This setting here is more general. Okay, so then you have the S polymorphisms, the S invariant relations forming a similar Galois connection, but the question is whether the Galois closed sets exactly characterize what you want them to characterize. And that's what we're going to look at next. The relational clones, first you have to define this notion of relational clone. In general, this is, of course, from clone theory right now. I need this notation for when I explain this for the S relational clones on the next slide. So for standard clones, if you have a set of relations on a finite set A, and it should contain, a relational clone is such a set which contains the identity relation, the actual binary identity relation, and it has to be closed under a different 5 operations, but the first 2 have the same name because they, again, just permute coordinates, cyclic shift and transposition. And they do it to, remember, relations, we think of them as having tuples as columns. So what's getting switched here is the rows. So this, and then PR is a projection where you are deleting the first row. So it's a projection on the remaining rows. And you can multiply, you can take the Cartesian product of two, an M-array relation and an M-prime array relation by just conjoining the tuples, and then you can also take the intersection, and if they have different arities, the intersection will just be empty, and sometimes you want to track the arity of the empty set too, but so this is slightly simplified here, but anyway, that if you close under all these, then you call the bunch of relations a relational clone, and there's again a notion of a relational clone being generated by a set of arbitrary relations, which will just be the least one that's closed, that contains this relation. And this, the theorem of the Paulin-Galois connection for clones is simply the observation. It's something that has a not obvious proof at all, but for finite A, well, first of all, polars of any subset of relations is a clone, and the invariant relations of a set of operations is a relational clone. But then the important thing is that in clone theory, if you do this over a finite set, the generation of a clone is obtained by taking first the invariant relations and then the polymorphisms of those. And the same thing happens on the relational side if you go the other way. So the Galois closed sets capture the notions that one is interested in. So with S relational clones and the S-Paul-in-Galois connection, you have to now do similar things, but with tuples of M-array relations. So these 5 operations here are applied more or less point-wise or coordinate-wise on the S tuples, exactly. For the first 3, 4 actually. And then for the meet, for the intersection, the meet is just an intersection if the signum is in capital S, which is the monoid, multiplied by T. That's an ideal of the monoid. T here is a parameter because in this definition, T just is an element of capital S. And this is called the ST intersection. And if you take T equal to the identity element of the monoid, then this is just the ordinary intersection. So that includes that intersection from clone theory, but it's slightly refined and allows intersection of a greater variety of things. And then here is something called index translation, which is also based on the monoid S by saying that mu sub T takes a S tuple of MRE relations and then switches them around according to how multiplying by the element T will modify the elements in the monoid. If it's a group, then that would be just a permutation. And the S relational clone generated by a set is the same idea. And then one can prove, first of all, that the Galois closed sets are of the right form. They give you things that have these properties, but you would like to know that you get all the things you care about. And so now this is a matter of how are they characterized. And first of all, the MRE diagonal relations can be defined in this way. And the MRE diagonal relations based on an equivalence element epsilon, I should say here, are defined like this. This is just to be able to capture the smallest relational clone generated by the binary identity relation. And in the S relational clones, we have the S diagonal relation concept, slightly modified. And this is the concept that you need to get the smallest S relational clone. And then also, if you generate and then take the polymorphisms, you get the same thing as if you just take the polymorphisms of the set R. And if you, the same thing on the functional side, if you find the invariant relations. So that's an important step here. And then for the functional side, we can show that if you take a collection of functions in the S operations, then this set, if you throw away the signum and you generate the ordinary clone, that's the same as if you first find the S invariant relations, look inside there, all the S invariant relations that have the same relation rho in each component of the S tuple, and then collect all those together and find their polar. So that's a connection between ordinary clone theory and the S clone theory, or the S pre-clone theory, I should say. Characterizing S pre-clones. This is a technical slide. I'll gloss over this a bit. You can't. This is how this gets done. Also in the clone theory case, the proof that something is closed. And that's what we down here is the big theorem that, at least for a functional side, the clone generated by a set F, the S pre-clone generated by a set F, is the S invariant relations of F followed by the S polymorphisms of F. And the proof is based on something similar to how you can do this for ordinary clones. This is like a graphical relation where if you have an algebra, this is why the set has to be finite. If A is finite, has k elements, you can form a matrix which is k to the n by n, and which lists all the n tuples of A, say in lexicographic order, and then preserving that relation tells you exactly how elements end up in the clone, in the S pre-clone generated by F. They are exactly those functions which preserve these graphical relations based on this chi lambda, which is defined here. And I'm going to run out of time if I don't ignore some of these details, but the slides will be available. And the interesting thing is that so far we've assumed S is a monoid, and we were able to prove this part here. But that was, at first we assumed that it's a group, and later realized that, and there are some applications where you don't want to only do this with groups. But for the other part here, we have to now assume that the sigma form a group, like in the plus minus case, where it's the two-element group, isomorphic to it. And well, then you get this second part also in general, but only for the group case and for, of course, for finite A. And that tells you now that the lattice of S pre-clones is exactly the lattice of Galois closed subsets of this Galois relation. And for group S of sigma, this lattice on the finite set A, the lattice of S relational clones, they're dually isomorphic. This is just standard Galois theory, but it's nice and that it holds again, and it's similar to the case for the clone theory. And now S3 clones, some properties about this lattice. The top is finitely generated, the top of the relational side is finitely generated, the lattice is atomic and coatomic, and there's finitely many atoms and coatoms. These are results from, they generalized from clone theory into this area, and then we started looking closely at the special case when you just have a small two-element set A, and those are called Boolean clones. Of course, this was originally described by Emil Post, and it has 5 maximal clones and 7 minimal clones, and there's a picture of it. And now the question is, well, what does it look like for S3 clones if you take the simplest case, which is still 2 elements in A and plus and minus? And I'm sorry to say I can't draw that picture yet, but it's also more complicated than this. Boolean plus minus clones, we use this plus minus notation. I'm going to gloss over it. We've seen this already. And here is a description of the 9 maximal Boolean plus minus pre-clones. So previously there were 5, and they come in, well, 5 of them are actually analogs of the ordinary 5 clones. And then there's these 4 additional ones. One of them is the one that has to do with order preserving and order reversing. It's one of the maximal ones. And the other 3 are other combinations of relations that are not too surprising, but that's it. And then on the minimal side, there are 23. And the way you can read them here is they're generated by certain functions, and the order of the variables here is x, y, z. And this is the signum, say, but there's only, here's 4 variables. Here the signum still has 4 things in it, but only 3 variables. Well, it means that you have a fictitious variable, which you can always add or delete, right? And so here you have more of them. There's 9 here, and then another 9 in this line. And together it makes 23. But of course, you can check that these are minimal. It's not that much work, but coming up with the argument that these are all of them is additional work, and certainly not something I can go over right now. Here are some questions that we would like to solve in the future. And this is the one that we've spent quite some time on already, but we don't know. And the hope is that it is countable. That's at least my hope, but I'm not going to make a conjecture. Because when you go to clones on 3-element sets, we know it's hopelessly uncountable. And here we're adding something significant to 2-element clones, making them into S3 clones over a pretty small signature. So classify all the maximal S3 clones the way Ivo Rosenberg did for clones, for example. Should be possible in some ways. And this question, if you have a monoid, can you still get this result, or is there a counterexample? That would also be interesting. And that's where I want to stop. Thank you very much. Oh, you wanted to ask a question, perhaps? I don't know.
No,
we're not hearing them.
Maybe
Where's
it
the
was
problem?
loud.
Been muted, but what's going on here? We don't even have a. Oh, no, we have volume here, and I don't think we're muted. But...
Reinhard, turn off mute.
Okay, if anybody wants to ask a question.
Yeah. Hello?
Yes, so no, the volume works. Thank you.
Is this okay? Do
Sure.
you want something from me? Thank you for your talk, Peter.
Thank you for being up at this late time.
Yeah, it's very late here.
Indeed.
Did you?
Okay, yes. So this result that you have where you showed there's some number of maximal elements and 23 minimal elements. Did you like compute that with a computer? Like how did you, that seems like a lot of casework.
Yes, I mean, we've checked some of the things with calculations in some small Python programs, but mostly it was done by hand. And
Wow.
by my colleagues. I was doing some of the programming.
Senior member of the team.
Yes, let me be honest. The project, I'm reporting on a preliminary version of all our results, and we're working furiously to finish this. But thank you. Yes.
So Peter, in the traditional relational clone, right, you gave one way of generating the
Yes.
relational clone. The relational clone. Another way to do it is through these positive primitive formulas.
Yes.
Have you tried to do the same thing?
Yes. As a team, we have. And it's promising.
Oh, Reinhardt's got contributing here.
Can you listen me?
Yes.
We can hear you.
Yeah, okay. I just want to say, yes, you can do this with the primitive positive formulas, but you have to do it for every component, so to say, for the S part, for each element of the monoids, you have a relation, and you have to apply the primitive positive formula to every this relations using the same formula. So it works more or less.
So we're getting to the situation where we have another group waiting. So how about if anyone wants to skip out and get to the next talk, then go ahead. And if we had a couple more questions here, then you can stay and ask. Okay? But if you want to go to the next talk, please feel free to go.
So here you indicate that the minimal and the maximal clones you have are obtained by mimicking some of the existing ones for the classical case. Can we do that for every clone?
This, yes, the lattice of clones is embedded in the lattice of S3 clones in several different ways. And we've looked at that. I just didn't have time to go over the details. So there's one embedding to the top, there's an embedding to the bottom. And the hope is that they will allow you to give an actual description of that lattice relative to the lattice of clones.
Any more questions? Okay, well, thank you.